Settle in now. Go ahead and find that position where your body feels most at ease, where the mattress meets your weight just right, where the pillow cradles your head in exactly the way you like, where the world outside begins to feel very, very far away. Let your shoulders soften. Let your jaw unclench. Feel the slow, gentle expansion of your rib cage with each breath in, and the quiet release as each breath drifts out. There's nowhere you need to be right now. Nothing that needs doing. This moment belongs entirely to you. Tonight, we're going to drift somewhere extraordinary together. Not to a faraway place on Earth, but beyond Earth entirely. Past the Moon, past Mars, past the outer rim of our solar system, and then even further still, until we're looking back across 13 billion years of cosmic history. We're going on a journey through one of the most profound scientific endeavors ever undertaken by our species, the James Webb Space Telescope. Before we begin, if you're finding value in these journeys through science and sound, a quiet like on this video means the world. And if you'd like these stories to find you each time you settle in, a gentle subscribe will make sure they do. Now, take one more slow breath. Let the outside world dissolve, and let the stars come in. Part 1. The Dream of Webb. Origins and Decades of Waiting. Long before there was a telescope, there was a question, and the question was breathtakingly simple. What does the beginning look like? Astronomers had been asking it for as long as they had had instruments powerful enough to even begin approaching it. The Hubble Space Telescope, launched in April of 1990 aboard the Space Shuttle Discovery, had given humanity its first genuinely clear window into the deep universe. Hubble was revelatory. The images it returned of distant galaxies, of glittering nebulae where stars were being born, of the ancient light that had crossed billions of light years to reach its mirror, were nothing short of transformative. They didn't just advance science. They changed the way our civilization understood itself. The Hubble Deep Field image, captured in December of 1995, by pointing the telescope at a seemingly blank patch of sky for 10 consecutive days, revealed approximately 3,000 galaxies in a region so small it would be covered by a grain of sand held at arm's length. 3,000 galaxies in a tiny sliver of darkness. The universe, that image declared quietly, is incomprehensibly full. Hubble kept going. Over the years, it was visited by astronauts 5 times, each time receiving new instruments and repaired components that extended its life and expanded its capabilities. The Hubble Ultra Deep Field, released in 2004 after 11 days of combined exposures, pushed deeper still, finding galaxies formed when the universe was only about 500 million years old. The Hubble Extreme Deep Field in 2012 pushed the record further, to objects existing perhaps 400 million years after the Big Bang, representing the first few percent of the universe's current age of 13.8 billion years. Each of these deep field campaigns was an act of extraordinary commitment. Weeks of precious observing time dedicated to staring at apparently empty sky, accumulating photons one by one until the first, faint light from the beginning of the cosmos could be coaxed out of the noise. And yet something remained stubbornly beyond reach. Astronomers knew, from calculations and from the structure of the cosmic microwave background, the faint afterglow of the Big Bang itself, that the universe must have gone through a period they called cosmic dawn. This was the epoch in which the very first stars ignited, in which the first galaxies assembled from primordial gas and dark matter, in which the universe was transformed from a cold, dark, neutral sea of hydrogen and helium into the lit, ionized cosmos we inhabit today. That transformation, the epoch of ionization, happened roughly between 300 million and 1 billion years after the Big Bang. Hubble could just barely scratch the surface of that epoch. The galaxies, forming at the heart of the cosmic dawn, those first fragile collections of stars, were simply beyond what visible light astronomy could see. Their light, redshifted by more than 10 in wavelength, lay entirely in the infrared. Reaching them required a fundamentally different instrument, but Hubble had its limits. It was designed to observe primarily in visible light, the same narrow band of the electromagnetic spectrum that our own eyes are sensitive to. It could push deeper into the universe than any telescope before it, reaching back to galaxies that existed when the cosmos was about 700 million years old. But beyond that, the light from even earlier galaxies was essentially invisible to Hubble, for a reason that would take a moment to explain but is worth understanding clearly, because it is the key that unlocks everything Webb would eventually do. The universe is expanding, not in the sense that it is expanding into something. There is no outer edge, no container it is growing inside. Space itself is stretching in every direction, carrying galaxies along with it, the way raisins in a rising bread dough move apart from one another as the dough grows. This expansion has been happening since the moment of the Big Bang, some 13.8 billion years ago, and it is not slowing down. Since the late 1990s, we have known that it is actually accelerating, driven by a mysterious energy pervading empty space that physicists call dark energy. Nobody knows what dark energy is. We only know what it does. It is causing the universe to expand faster and faster, pulling distant galaxies away from us at speeds that, for the most remote ones, exceed the speed of light itself. This expansion has a profound consequence for light. When light travels across expanding space, its wavelength gets stretched too. Think of drawing a wave on a rubber band and then pulling the rubber band longer. The wave gets drawn out, the distance between its peaks increases. Longer wavelengths in light correspond to redder colors. Shorter wavelengths correspond to bluer ones. So, as light travels across the expanding universe over vast distances, it shifts toward the red end of the spectrum, a phenomenon called redshift. The farther a galaxy is, the more its light has been stretched, and the oldest, most distant galaxies, those that formed when the universe was only a few 100 million years old, have had their light stretched so dramatically that it has been pushed entirely out of the visible range. That ancient light, which began its journey as ultraviolet radiation from blazing young stars, arrives at Earth today as infrared radiation, heat, completely invisible to our eyes and to Hubble's detectors. This was the wall that astronomers had been staring at since Hubble first opened its eye. They knew galaxies existed beyond that wall. They could infer them, theorize about them, sketch out what they might look like based on computer models and the physics of the early universe. But seeing them? Actually observing the stars that first lit up in the cosmic dawn in those first few 100 million years after the Big Bang? That required a different kind of telescope entirely. One built not for visible light, but for infrared. One cold enough, and large enough, and sensitive enough to capture those ancient photons that had been traveling for more than 13 billion years. The idea that would eventually become the James Webb Space Telescope was first seriously proposed in 1996, following a report from a committee convened to think about what should come after Hubble. The report, written by a group of astronomers that included Garth Illingworth and others who would eventually become central figures in Webb's science program, outlined a bold vision. A telescope with a mirror somewhere between 4 and 8 meters across, orbiting far from Earth's warmth, capable of seeing the very first galaxies. At the time, it was more ambition than blueprint. The engineering challenges were nearly fictional in their scale. Hubble's mirror is 2.4 meters across, roughly the diameter of a large dining table. To improve substantially on its ability to collect infrared light, the new telescope would need a mirror perhaps 6 meters across. The problem is that a mirror 6 meters in diameter cannot fit inside any existing rocket fairing. The only solution was to build the mirror in sections, like a compound eye, that could fold up for launch and then unfold precisely in space. And the mirror couldn't just unfold. It had to unfold to tolerances measured in nanometers, hundredths of the width of a human hair, in the vacuum and cold of space, more than 1 million miles from Earth, with no possibility of a service mission if anything went wrong. The precision required was, at the time, beyond anything that had been demonstrated in engineering. The team would literally have to invent it. Then there was the matter of temperature. Infrared telescopes must be cold, extremely cold, to function. A warm telescope emits its own infrared radiation, which would swamp the faint signals from distant galaxies the way a lit match would be invisible in the beam of a spotlight. Hubble orbits Earth at about 570 kilometers altitude, cycling in and out of sunlight every 96 minutes. That kind of thermal cycling makes extreme cold essentially impossible to maintain. The new telescope would need to be stationed somewhere stable, somewhere it could keep its cold side perpetually pointed away from the Sun, the Earth, and the Moon. The location chosen was the Sun-Earth L2 Lagrange point, a gravitational equilibrium spot roughly 1.5 million kilometers away from Earth, about 4 times the distance to the Moon, on the opposite side of Earth from the Sun. At L2, a carefully designed sunshield could block all incoming light and heat from the Sun, Earth, and Moon simultaneously, allowing the telescope's mirror and instruments to cool passively to around negative 223 degrees Celsius, cold enough to make the infrared universe visible. What followed was roughly 2.5 decades of the most ambitious and prolonged engineering program in the history of civilian astronomy. The telescope was named for James E. Webb, the NASA administrator who oversaw the Apollo program during its formative years in the 1960s, and was a fierce champion of space science. Construction was led by NASA's Goddard Space Flight Center in Greenbelt, Maryland, with major industrial contributions from Northrop Grumman, who was responsible for the spacecraft bus, the sunshield, and the mechanical systems, and a deep international partnership with the European Space Agency and the Canadian Space Agency. The mirror segments were carved from beryllium, a lightweight, extremely rigid metal that retains its shape even at cryogenic temperatures, and coated with a layer of gold about 100 nanometers thick to maximize infrared reflectivity. All 18 hexagonal segments were polished to a smoothness that, if scaled up to the size of the continental United States, would have no hills or valleys more than a few inches tall. The polishing of the beryllium mirror segments was done at a facility in Litchfield Park, Arizona, using a technology called ion beam figuring. Charged particles were directed at the mirror surface and removed material atom by atom, sculpting the final shape with precision that had never been required of any manufactured surface at this scale. Once polished, Each segment was tested at cryogenic temperatures in a specialized facility, because beryllium, like all materials, changes shape as it cools. The mirror's final shape at negative 220 degrees Celsius had to be precisely known, and its room temperature shape was calculated backward from the required cold shape, meaning the engineers were effectively polishing a mirror into a shape that was slightly wrong at room temperature, knowing it would become exactly right in the cold of space. The sunshield was a marvel of its own kind. 5 layers of a material called capton, each coated with reflective aluminum and separated from one another by slender spacers that allow heat to radiate away from the gaps, arranged like the membranes of a living thing. Folded up for launch, the sunshield occupied roughly the volume of a wardrobe. Deployed, it stretched to the size of a tennis court. Each of its 5 layers operates at a progressively lower temperature, with the sun-facing side reaching over 80 degrees Celsius and the cold side, the telescope side, dropping below negative 223 degrees Celsius. The temperature difference between the two sides of the sunshield is more than 300 degrees Celsius, occurring across a distance of only about 5 meters. Designing a structure that remains dimensionally stable and correctly tensioned across such an extreme gradient, while also surviving the violence of launch, was one of the most technically demanding aspects of the entire program. The program was beset by delays and cost overruns so severe that the telescope was nearly canceled by the United States Congress in 2011. At that point, roughly $6 billion had already been spent, and the projected final cost had ballooned to something approaching $10 billion. Senator Barbara Mikulski of Maryland, whose state housed the Goddard Space Flight Center and the Space Telescope Science Institute, fought particularly hard for the program's survival during those dark months. The scientific community mobilized with something approaching desperation. Astronomers who had built careers around the telescope's promises, who had designed instruments for it, who had written proposals for its observing time, understood viscerally that its cancellation would be a generational wound to the entire field of astronomy. The telescope survived. But the launch date, originally projected for 2011, was pushed back again and again to 2014, then 2018, then 2020, then 2021. Every delay was genuinely painful. Some of the scientists who had contributed foundational ideas to the mission retired before it ever flew. Some died. The telescope they dreamed of launched on Christmas Day, 2021. That Christmas morning, from the Guiana Space Center in Kourou, French Guiana, an Ariane 5 rocket carrying the folded, bundled, carefully protected James Webb Space Telescope lifted from the launch pad and climbed through the atmosphere with what Space.com's coverage team described as a nearly flawless flight. The launch window had been precisely calculated. The trajectory was precise. The orbit injection was almost exactly on target, which had a consequence that would only become apparent later. The spacecraft used significantly less fuel than planned during its journey, leaving it with fuel reserves potentially sufficient for 20 years of orbital station keeping, rather than the planned 10. Astronomers who had waited decades for this telescope learned that it might serve them for twice as long as they had hoped. It was a Christmas gift on top of a Christmas gift. For the next month, Webb was a nerve-wracking origami act performed in slow motion at a distance of more than 1 million kilometers. The sequence of deployments had been designed, tested, and rehearsed on Earth for years, but there was no rehearsal for doing it in space. The solar array deployed within minutes of separation from the rocket. the high-gain antenna extended. Then, 2 days after launch, the sunshield began to unfold, a sequence of multiple separate steps, each involving different motors and tension systems that stretched over several days. The 5 layers had to deploy in order, each separating from the previous and being tensioned correctly. If any single deployment step failed, any one of the hundreds of individually critical mechanisms, the telescope might never reach its operating temperature, and the mission would be over. Every deployment step was announced by mission controllers at the Space Telescope Science Institute in Baltimore and at NASA Goddard. Every success was cheered. The world, watching via live streams and NASA social media updates, waited with the team through each critical milestone. The secondary mirror deployed, the aft momentum flap locked into place. The primary mirror's 2 wing sections swung outward and latched, bringing the 18 hexagonal segments to their initial positions. In the 2 weeks following launch, all of the major structural deployments succeeded. Not one failure, not one anomaly that required more than routine corrective procedure. The mirror alignment that followed was a months-long process of extraordinary delicacy. Once the instruments had cooled sufficiently for their infrared detectors to function, Webb began sending back its first light. Images of 18 separate blobs of light, each one a defocused image of the same star, one from each mirror segment. Over the following weeks, the mirrors were actuated by tiny motors. 6 actuators per segment, plus a central degree of freedom, making adjustments measured in nanometers, smaller than the wavelength of visible light, until all 18 images resolved into one. The final wavefront error of the aligned mirror was approximately 70 nanometers, well within specifications and representing, as one participant later described it, a level of precision that would have seemed impossible a decade earlier. The first engineering images, released in March of 2022 to demonstrate that alignment was underway, showed a pattern of 18 separate images of the same star gradually being brought into focus. The final alignment image showed a single, perfectly resolved star, surrounded by the faint, unmistakable smear of distant background galaxies, caught effortlessly, without even being the target. The team understood immediately that the telescope's optics were performing beyond their best expectations. The images were sharper than the specification required. The sensitivity was higher than the specification required. Webb, after 25 years of preparation and 3 decades of waiting, had arrived at its destination and was performing beautifully. By June of 2022, science commissioning was underway. The instruments were cold, aligned, and calibrated. The ground systems were tested. The pointing precision was verified to be within 2 milliarc seconds, the apparent width of a human hair seen from roughly a kilometer away. After 25 years, after the combined working effort of thousands of engineers, scientists, and support staff across a dozen countries, the James Webb Space Telescope was ready to open its eye on the universe. Part 2. The Engineering Marvel. How Webb Actually Works. To appreciate what Webb sees, it helps to understand what it actually is, not just at the level of numbers, but at the level of concept. What does it mean to see the universe in infrared? Why does that matter so profoundly? And what does this instrument, alone in space more than 1 million kilometers from home, actually do each time it turns toward a target? Start with light itself. The light we see with our eyes, what physicists call the visible spectrum, occupies a narrow band of wavelengths roughly between 380 and 700 nanometers. Violet light has the shortest wavelength. Red light has the longest. Just beyond red, with wavelengths too long for our eyes to detect, lies the infrared. And just beyond the visible toward shorter wavelengths lies the ultraviolet. These are all the same phenomenon, electromagnetic radiation, differing only in the length of their waves. Radio waves, microwaves, infrared, visible, light, ultraviolet, X-rays, and gamma rays are all fundamentally the same kind of wave. Our eyes are simply tuned to a tiny slice of that spectrum, optimized by millions of years of evolution to see the peak output wavelengths of our particular host star. Every object in the universe that has temperature emits radiation. The hotter an object, the shorter and more energetic its radiation tends to be. The Sun, with a surface temperature of about 5,777 degrees Celsius, emits most of its light at visible wavelengths, which is why our eyes evolved to see invisible light, and why daylight is the way it is. Cool stars, much less massive and less hot, emit most of their energy at infrared wavelengths. Planets, which are warm but far cooler than stars, emit almost exclusively in infrared. Gas clouds, star-forming regions, and newly forming planetary systems, all embedded in dust that absorbs visible light but is transparent to infrared, can be penetrated by infrared observations. The infrared sky is full of things that are completely invisible in visible light. Brown dwarfs, forming solar systems, the warmth of gas in the cold regions between galaxies, and the ancient light of the first galaxies, redshifted from ultraviolet into infrared over billions of years of cosmic expansion. Webb was designed with 4 scientific instruments, each serving different purposes across the infrared wavelength range. The near-infrared camera, called NIRCam, is the primary workhorse. Built by a team at the University of Arizona and Lockheed Martin's Advanced Technology Center, it captures images from about 0.6 to 5 microns in wavelength, covering from the very red edge of visible light well into the near-infrared. NIRCam is what produces the sweeping, glittering images of nebulae and distant galaxies that have captured the world's imagination. It has a dual-channel design, observing short and long infrared wavelengths simultaneously, and can survey large areas of sky in multiple color filters all at once. Its detector arrays are arrays of mercury-cadmium telluride, a semiconductor material that becomes electrically sensitive when struck by infrared photons. The near-infrared spectrograph, called NIR-SPEC, is provided by the European Space Agency. Where NIRCam shows how objects look, NIR-SPEC shows what they are made of. By spreading the light from a target into a spectrum and measuring the precise wavelengths at which different chemical elements absorb or emit radiation. Each element has a unique spectral fingerprint, as distinctive as a human fingerprint. Hydrogen absorbs at specific wavelengths, oxygen at others. Carbon, nitrogen, silicon, calcium, each has its own signature, a set of wavelengths at which its electrons can jump between energy levels by absorbing or emitting photons. NIR-SPEC is equipped with a microshutter assembly, an array of about 250,000 tiny doors, each about 100 by 200 microns in size, that can be opened or closed individually. By opening specific shutters that correspond to the positions of selected targets on the sky, NIR-SPEC can obtain spectra of up to 200 objects simultaneously, dramatically accelerating the pace at which distant galaxies can be characterized. The Mid-Infrared Instrument, called MIRI, is a joint production between NASA's Jet Propulsion Laboratory and a consortium of European institutes across 9 countries. It operates at longer infrared wavelengths, from about 5 to 28 microns. At these wavelengths, dust glows. Cosmic dust grains heated by nearby stars, or by the radiation of the early universe, re-radiate their absorbed energy at mid-infrared wavelengths, and Webb can see directly into star-forming regions that are completely opaque to NIRCam and to Hubble. MIRI can also study the warmth of planets in our own solar system, the chemistry of molecular clouds, and the spectral, energy distributions of galaxies at wavelengths that reveal their dust content and star formation histories. MIRI requires an even colder operating temperature than the other instruments, not just the passive cooling provided by the sun shield, but an active refrigeration system, a small mechanical cryocooler that continuously chills MIRI's detectors to just 7 degrees above absolute zero, or negative 266 degrees Celsius. The fourth instrument, the Near-Infrared Imager and Slitless Spectrograph called NIRISS, is a Canadian contribution provided by the Canadian Space Agency. NIRISS excels at several specific observation modes, including characterizing the atmospheres of exoplanets through transit spectroscopy, measuring the precise ways in which a planet's atmosphere filters starlight as the planet passes in front of its star. NIRISS can also perform what is called aperture masking interferometry, blocking most of the primary mirror and using only a carefully chosen subset of the aperture to create interference patterns that reveal fine structure very close to bright stars, potentially detecting companion stars or massive planets near their hosts. The primary mirror, at the heart of all of this, is the collecting area that makes everything possible. With 18 hexagonal segments, each measuring 1.32 meters across, the assembled mirror spans 6.5 meters and has a total collecting area of approximately 25.4 square meters. That is more than 6 times the light collecting area of Hubble, which at 2.4 meters in diameter collects light across about 4 square meters. In practical terms, this means Webb can detect objects roughly 100 times fainter than Hubble could, and can do in 12 hours what would have taken Hubble weeks. The gold coating on each segment provides exceptional reflectivity for infrared wavelengths. Gold is chosen not for its symbolic value, but because it reflects infrared light better than almost any other practical material, with reflectivity exceeding 98% across the relevant wavelength range. The L2 orbit deserves a moment of reflection too, because it is one of the more elegant aspects of the telescope's design. The Lagrange points are 5 specific locations in the Sun-Earth gravitational system where the gravitational pulls of the Sun and Earth combine with the centripetal effects of their mutual orbit to create stable or semi-stable regions, where a spacecraft can maintain its position using very little fuel. L2 is located exactly opposite the Sun from Earth, about 1.5 million kilometers further out in the solar system. At L2, the Sun, Earth, and Moon are always on the same side of the spacecraft, perfectly positioned to be blocked all at once by the sun shield. Webb orbits in a halo path around L2, a gentle, slow loop that keeps it roughly in position while allowing it to see any part of the sky not obscured by its sun shield over the course of a year. On any given day, Webb can observe about 40% of the entire sky. Over a year, it can observe any target that isn't too close in angle to the Sun, Earth, or Moon. The accessible sky is enormous. The decision to locate Webb at L2 rather than in low Earth orbit like Hubble meant accepting one profound consequence. This telescope can never be serviced. Hubble was visited 5 times by Space Shuttle astronauts who replaced instruments, repaired components, and most famously corrected the famous mirror flaw discovered after its 1990 launch, when a polishing error had left the mirror's shape off by less than 1/10 the width of a human hair, enough to make every Hubble image initially blurry before corrective optics were installed in 1993. Webb, 1.5 million kilometers away, is beyond any conceivable repair mission. It either works perfectly from the moment it deploys, or it doesn't work at all. This is why the engineering had to be so extraordinarily meticulous, why the testing was so comprehensive, why every component was subjected to simulations of launch vibration and thermal cycling and vacuum exposure. The telescope that launched on Christmas Day, 2021, was the most thoroughly tested spacecraft in history. And when it arrived at L2 and began to unfold itself, it worked. Everything worked. In a program of that complexity, spanning a quarter century, that outcome was neither inevitable nor to be taken for granted. Part 3. The First Light, July 2022, and the world caught its breath. The date was July 11th, 2022. It was a Monday. In the East Room of the White House in Washington, President Joe Biden stood before an image on a large screen and said, "These images are going to remind the world that America can do big things. And they remind the American people, especially our children, that there's nothing beyond our capacity." The image he unveiled was Webb's first deep field, a region of sky centered on a galaxy cluster called SMAC0723, which lies about 4.5 billion light-years from Earth. The image covered a patch of sky so small it would be blocked by a grain of sand held at arm's length. And within it, thousands of galaxies. Not just the cluster galaxies in the foreground, with their soft, elliptical glow and gentle halos, but background galaxies behind the cluster. Galaxies so distant their light had been traveling for more than 13 billion years to reach the high telescope. Many of them were bent into graceful arcs by the gravitational lensing effect of the cluster's mass. Their light curved around the foreground galaxies, like streams flowing around stones in a river. The same galaxy appeared multiple times in the image, its light having taken different paths around the intervening cluster. The image had required only about 12.5 hours of total exposure time. In that same amount of time, Hubble would have captured a fraction of the detail. Looking at the image carefully, you can see galaxies of extraordinary variety. Young spiral galaxies, their disk structures distorted by the gravitational tidal forces of the cluster. Ancient elliptical galaxies, reddened by their age, mostly composed of old stars that formed when the universe was young. And behind everything, the background galaxies, small, distorted, faint, some of them existing as they were when the universe was less than 1 billion years old. The image was a record player of cosmic time, with the tracks laid down at different distances and therefore different epochs, all playing simultaneously on a single screen. Within hours, the image was everywhere. It appeared on television screens and phone screens and newspaper front pages across the world. Scientists who had spent their careers contributing to the telescope were photographed with hands over their mouths, tears on their faces, expressions that combined profound satisfaction with something that could only be described as wonder. The engineering had worked. The science had begun. the world had one evening to sit with that image before NASA released the full suite of Webb's first science images on July 12th. And those images, 5 separate targets, chosen to demonstrate the full range of Webb's capabilities, arrived like chapters of an unexpected book, each one revealing something that cameras had never quite seen before. The image of the Carina Nebula was perhaps the most immediately striking to the general public. The Carina Nebula is a star-forming region about 7,600 light-years away in the southern constellation Carina, and it had been photographed many times by Hubble and ground-based telescopes. It was not unknown. But the version that Webb's NER-CAM returned was something else entirely. What had appeared in earlier images as a wall of opaque dust and gas, an impenetrable brown and gray curtain, was revealed in infrared light to be a landscape of astonishing complexity. Spires of gas towering several light-years high, speckled with previously hidden young stars. What looked like mountains and valleys in some moonlit alien terrain. Hence the name the team gave this region, the Cosmic Cliffs. The tallest of those apparent mountains, composed of dense gas being sculpted by the ultraviolet radiation and stellar winds of massive young stars located above and to the right of the image frame, rises about 7 light-years. 7 light-years is roughly 1.5 times the distance from our Sun to the nearest star system. These are not small features. The entire structure depicted in the image spans roughly 8 light-years across, an area far larger than the distance from our Sun to its nearest neighbors. The steam rising from the crests of these formations is not steam at all, but hot, ionized gas streaming away from the nebula's surface under bombardment from nearby stars. Hundreds of stars that had never been seen before, hidden inside their cocoons of dust, invisible to Hubble's visible light instruments, appear in Webb's infrared image as orange and red pinpoints, newborn suns in the earliest stages of their existence. Some emit jets visible in the NIR-CAM image as orange streamers punching outward from star-forming regions, still embedded in the dusty material from which the stars themselves are forming. The entire image has the quality of a painting by someone who understood both deep physics and deep beauty simultaneously. The MIRI companion image of the same region added another dimension entirely. Where NIR-CAM showed the landscape in near infrared, revealing the stars and the gas structures and the jets, MIRI's mid-infrared view showed the dust glowing with its own thermal emission. Features that looked like solid walls of rock in the NIR-CAM image became translucent in the MIRI view, with the internal structure of the dust clouds visible as if lit from within. Some sources that appeared as stars in NIR-CAM revealed themselves in MIRI as point sources embedded in disks of circumstellar material. Young stars still in the process of assembling, surrounded by the raw material from which their own planetary systems may one day form. A feature at the left of the image that appeared to NIR-CAM as a comet shape was revealed by MIRI to be one cone of an outflow from a dust-enshrouded newborn star. The star itself invisible to NIR-CAM, but its thermal signature clear and bright in MIRI's longer wavelengths. Stephan's quintet, a grouping of 5 galaxies in the constellation Pegasus, was another of the first light targets. 4 of the 5 are bound together by gravity in a cosmic dance of collision and interaction, their spiral arms being drawn out and distorted as they pull on one another. The 5th, actually much closer to us at only 40 million light-years compared to the group's 290 million light-years, merely appears nearby in the sky due to the geometry of our line of sight. Webb's image of this system contained over 150 million pixels and was assembled from almost 1,000 separate exposures. Visible in the image are threads of gas and dust connecting the colliding galaxies, star-forming regions sparked by the compression waves of the collision. The glowing hearts of each galaxy with their dense concentrations of old stars, and the enormous shock wave created where one galaxy plows through intergalactic gas at hundreds of kilometers per second. At the center of one galaxy in the group, NGC 7318b, a shock wave of hot gas spans about 100,000 light-years, larger than our entire Milky Way. The image captures not just a moment, but a process. Hundreds of millions of years of gravitational interaction. Its effects spread across the frame in arcing tidal streams and distorted spiral arms and the hot glow of shocked gas. The Southern Ring Nebula, known more formally as NGC 3132, was photographed in both near-infrared and mid-infrared, and the two images together told a story about a star in its final moments. A planetary nebula, the gas shell ejected by a dying star. The Southern Ring had been studied before. Its central star, a dim white dwarf surrounded by expanding rings of gas, was known. But Webb's images revealed something unexpected. A second star at the center, a brighter companion to the dying white dwarf, wrapped in a thick cocoon of dust that had escaped notice in previous observations. The NIRCam image showed the two central stars clearly, while the MIRI image showed the dust around the white dwarf in extraordinary detail. A complex, irregular shroud of material being expelled in the final gasps of a star's nuclear life. The outer rings of the nebula, each representing a separate episode of gas expulsion, as the dying star pulsed and shed its outer layers over thousands of years, showed in Webb's images a molecular complexity invisible to previous telescopes. In the cool gas of the outer rings, molecular hydrogen and carbon-based molecules were detectable by their spectral signatures. The star's last breath enriching the space around it with the raw materials of future planetary systems. And then there was the spectrum of WASP 96b, perhaps the least visually dramatic of the first releases, but arguably the most scientifically profound in what it promised. WASP 96b is a gas giant exoplanet, a world about half the mass of Jupiter orbiting a sun-like star about 1,100 light-years away. It completes one orbit every 3.5 days, and as it transits, passes in front of its star, a tiny fraction of the star's light filters through its atmosphere on its way to Earth. Webb's NIRIS instrument watched that transit and obtained a spectrum that revealed not just water vapor, but features consistent with clouds and hazes at various altitudes in the planet's atmosphere. Different pressure levels, different temperatures, different molecular compositions, all reading out in the wavelength-dependent dimming of the star's light as seen through the planetary atmosphere. It showed the fingerprints of molecular processes occurring in another world's sky at a level of detail never before achieved. And WASP-96b is not even an interesting target from an astrobiology perspective. It is far too hot and large to harbor anything like life. But it demonstrated, beyond any doubt, that Webb could read the atmospheric diaries of planets, which meant that, eventually, Webb could read the atmospheric diaries of smaller, cooler, potentially habitable worlds orbiting in the gentle warmth of their stars' habitable zones. Part 4. The Language of Light. Redshift and Looking Back in Time. Before we can fully appreciate what Webb has found in the most distant reaches of the observable universe, we need to sit with one of the most remarkable facts in all of science, that a telescope is also a time machine. Light travels at approximately 299,792 kilometers per second in a vacuum. This is the fastest anything in the universe can travel, not as a practical limitation of our technology, but as a fundamental law of nature. Nothing with mass can reach this speed. It takes infinite energy to accelerate mass to the speed of light, which means that only massless things like photons can travel at this velocity. It is a finite speed. This means that when you look at something distant, you are not seeing it as it is now. You are seeing it as it was when the light that is now reaching your eyes first departed. You look at the moon, and you see it as it was about 1¼ seconds ago. You look at the sun, and you are seeing it as it was 8 minutes ago. So, if the sun were somehow to vanish at this moment, we would continue to see it for another 8 minutes before the light stopped arriving. The nearest star, Proxima Centauri, appears to you as it was 4¼ years ago. Andromeda, 2.5 million light-years away, as it appeared 2.5 million years ago, when our ancestors were early hominins, before our species had emerged. The light reaching you from the farthest objects Webb can see has been traveling for more than 13 billion years. It left its source in the earliest epoch of the universe, when the cosmos was barely past its infancy, and it has been crossing the expanding gulf of space ever since. Every photon that strikes Webb's mirror from those most distant galaxies is a messenger from a time before our solar system existed, before Earth formed, before the atoms in our bodies had been forged in stellar nucleosynthesis. These photons are older than our world. This is not a limitation. It is a gift. It means that telescopes like Webb are not just observing space. They are observing history. By looking at increasingly distant objects, we are looking at progressively earlier epochs of the universe. We can, in principle, trace the evolution of stars and galaxies from the present day all the way back to the first few 100 million years after the Big Bang. If only we have instruments sensitive enough to see that far. And by comparing galaxies at different distances and therefore different cosmic ages, we can see directly how galaxies change over time, how they grow, how they merge, how their star formation rates rise and fall, how their chemical compositions evolve as successive generations of stars enrich the gas with heavy elements. Astronomers measure redshift using a dimensionless quantity called Z. A galaxy at redshift Z equals 1 is 1, where the universe has doubled in size since its light was emitted. Its light has been stretched to twice its original wavelength. At Z equals 2, the universe was 3 times smaller when that light departed than it is today. At Z equals 6, the universe was 7 times smaller. At these redshifts, astronomers are looking at galaxies existing when the universe was roughly 1 billion years old. During the epoch of Rayonization, when the first generation of galaxies was pouring ultraviolet light into the surrounding intergalactic hydrogen, breaking those atoms apart and ionizing the cosmos for the second time in its history. The cosmic timeline, understood in its broad strokes, is this. The universe began in the Big Bang approximately 13.8 billion years ago. A moment not of explosion into existing space but of the creation of space itself, along with time, matter, and energy, in conditions of infinite temperature and density. For the first few 100,000 years, the universe was so hot and dense that photons and matter were coupled together, unable to travel independently. Then, as the universe expanded and cooled, matter and radiation decoupled. Electrons combined with protons to form neutral hydrogen atoms, and the universe became transparent for the first time. The light released at that moment of decoupling is what we now detect as the cosmic microwave background radiation, the faint heat signal that fills the entire sky and carries the imprint of the universe's earliest structure. After decoupling, the universe entered what astronomers call the Dark Ages, a period of hundreds of millions of years in which there were no stars, no galaxies, no sources of light at all. Just cooling hydrogen and helium gas, slowly coalescing under the influence of dark matter's gravity, beginning to form the seeds of future cosmic structure. Then, somewhere around 100 to 200 million years after the Big Bang, the precise timing is still debated and being refined by Webb's data, the first stars ignited. These were nothing like the stars we know. They formed from gas with almost no heavy elements, no carbon, no oxygen, no silicon, and as a result, they were able to grow to sizes that would be impossible today. Theoretical models predict that the very first stars, called population 3 stars, may have been hundreds of times the mass of our Sun. They burned brilliantly and briefly, living perhaps only a few million years before exploding as supernovae and seeding the surrounding gas with the heavy elements that subsequent generations of stars would incorporate. The light from these first stars began ionizing the surrounding hydrogen, creating bubbles of ionized gas that expanded, overlapped, and eventually coalesced into the fully reionized intergalactic medium we see today. The epoch of reionization was the universe's adolescence, turbulent, creative, transformative. The JWST program was designed explicitly to map this epoch with a completeness never before possible. The JWST team pursued it from two complementary directions: broad, moderately deep imaging of large areas to find many galaxies at once and build statistical samples, and ultra-deep imaging of smaller fields to find the rarest, most extreme objects, the very first, most distant galaxies at the edge of Webb's reach. The two fields chosen, Goods South and Goods North, had been studied by Hubble and ground-based telescopes for decades, building up deep databases of galaxy positions, colors, and distances. JWST's Webb data built on this foundation, adding infrared wavelengths and sensitivity that Hubble could not match, and revealing thousands of galaxies that had been either invisible or ambiguous in the pre-Webb data. Spectroscopic confirmation is the gold standard in this field. A photometric redshift, estimated from the galaxy's colors in imaging data, is useful for identifying candidates, but it carries uncertainty. A spectroscopic redshift, obtained by actually dispersing the galaxy's light into a spectrum and measuring the wavelengths of specific spectral features, is definitive. NIR spec, with its ability to observe up to 200 galaxies simultaneously in spectra, transformed the rate at which spectroscopic redshifts could be obtained for faint, distant galaxies. A single NIR spec observation lasting 10 hours could confirm distances to dozens of galaxies that would each have required separate, time-consuming observations with previous spectrographs. The JWST team used this capability to build the largest spectroscopically confirmed sample of galaxies at the epoch of reionization ever assembled. When JWST scientists obtained a spectrum of the object that would become JADS-GS-Z 14-0 in January 2024, Exposing for nearly 10 hours with NIRS-PEC, they found that the Lyman alpha break, the sharp edge in the spectrum where neutral hydrogen absorption extinguishes light below a certain wavelength, was sitting at a position corresponding to a redshift of 14.32. The shattering of the previous record was, in Carniani's later description, unambiguous. The previous record holder, JD's GSZ 13.0, had been at a redshift of 13.2. The new galaxy was at 14.32. The universe, when the light from JD's GSZ 14.0 departed, was only about 290 million years old. Part 5. The most distant galaxy ever seen. Jade's GSZ 14.0. Kevin Hainline of the University of Arizona would later describe first seeing the confirmed distance of JD's GSZ 14.0 as one of the strangest and most wonderful moments of his scientific career. He compared it to finding a cell phone among ancient ruins in Rome, an object so sophisticated that its existence in that context makes no sense under any of the frameworks you had prepared for. The galaxy shouldn't have been the size it was. It shouldn't have been as bright. And it absolutely, definitively, should not have had oxygen. The galaxy, now known as JD's GSZ 14.0, was first noticed in imaging data from 2023. The JD's team had conducted deep NIRCam observations in October of that year, building what they called the JD's Origins Field, the most sensitive infrared image of any patch of sky ever taken, accumulated over 5 full days of telescope time. Within those images were numerous candidate high redshift galaxies selected based on their colors in different filters. JD's GSZ 14.0 appeared among them as a small reddish smear, but a reddish smear that was disturbingly bright for something supposedly so far away. The problem was that JADES GSZ 14.0 sat on the sky very close to another, unrelated foreground galaxy. The two appeared separated by less than half an arcsecond, which is a tiny angle. The JD's team was initially cautious about the high redshift interpretation because the proximity of the foreground galaxy could conceivably have contaminated the photometric measurements. There was a real possibility, for some months, that what they were seeing was not a galaxy at redshift 14, but a heavily reddened galaxy at a much lower redshift, its colors distorted by unusual dust or exotic stellar populations, and that it was actually a neighbor of the foreground object rather than a distant background target. Additional observations clarified the picture. Multiple NIRCam filter measurements, including observations in 7 medium-band filters from the JD's Origins Field program, made the low redshift interpretation increasingly implausible. Then, JD's researcher Jake Helton of the University of Arizona and Steward Observatory identified something remarkable. JD's GSZ 14.0 was also detected by Webb's MIRI instrument, operating at mid-infrared wavelengths. Given the galaxy's extreme distance, those MIRI wavelengths correspond to light that was originally emitted in the visible part of the spectrum, wavelengths that have been stretched by a factor of 15 over their journey across 13 billion light-years. The brightness of the source in the MIRI data was actually higher than a simple extrapolation from the NIRCam data would predict, suggesting the presence of strong emission lines, specific spectral features produced by ionized hydrogen and oxygen, that were boosting the light at those wavelengths. The spectroscopic confirmation came in January 2024, when NIR-SPEC was trained on the target for nearly 10 hours. The resulting spectrum left no room for interpretation. A precise redshift of 14.32 was measured from the Lyman alpha break, with supporting spectral features including emission lines from ionized hydrogen and oxygen. The spectrum matched a galaxy existing approximately 290 million years after the Big Bang. When the data was first processed, the team exchanged messages containing what Carniani later described as many exclamation marks. The previous record holder, JWST 13.0, had been at a redshift of 13.2. This new galaxy was significantly further and several times more luminous. That luminosity was deeply puzzling. Bright galaxies exist because they have many stars, many luminous stars, formed at high rates. But for this galaxy to contain the number of stars implied by its brightness, formed within the first 300 million years of the universe's existence, required star formation to have proceeded at a pace that the then standard models of early galaxy formation struggled to accommodate. From the imaging data, the galaxy was measured to span over 1,600 light-years in diameter. That's a substantial size, large enough, in fact, that the team concluded the light was not coming primarily from the central region of the galaxy, where gas accreting onto a supermassive black hole might produce a quasar. The emission was spread across the galaxy. It was coming from stars. The presence of oxygen was the most startling finding of all. Normally, the first galaxies in the universe are expected to contain almost exclusively hydrogen and helium, the two elements produced in the Big Bang. Heavier elements like carbon, nitrogen, oxygen, and iron, which astronomers collectively call metals, are manufactured inside stars through nuclear fusion and released into space only when those stars die. The process takes time. Massive stars live fast and die young, in millions of years rather than billions, producing supernovae that scatter their heavy element contents into the surrounding interstellar medium. But even at the speed of these stellar life cycles, for a galaxy to have built up a significant abundance of oxygen by only 300 million years after the Big Bang required multiple generations of stars to have already formed, lived, and died before we were observing it. When, in early 2025, two independent teams of astronomers using the Atacama Large Millimeter Array in Chile, known as ALMA, confirmed the detection of an oxygen emission line from JWST 14.0. The scientific community had to pause and reconsider its timetable for everything. ALMA's detection was precise enough to refine the galaxy's distance measurement to an uncertainty of just 0.005%. The galaxy's oxygen abundance, inferred from the emission line strength, was roughly 10 times higher than any model of early galaxy chemistry had predicted for an object at this epoch. The conclusion was inescapable. Multiple generations of very massive stars had already formed, burned through their fuel, and exploded as supernovae before JWST 14.0 came into our view. The universe was building chemical complexity faster, far faster, than anyone had calculated. One of the researchers on the ALMA oxygen detection, Sander Schouws, a PhD candidate at Leiden Observatory in the Netherlands, expressed the situation memorably. It was, he said, like finding an adolescent where you would only expect babies. The galaxy was not a primitive, freshly assembled collection of primordial gas. It was already, in the cosmic sense, mature, chemically enriched, luminous with stars, possessed of structures and compositions that were supposed to take far longer to develop. JWST 14.0 is now the most distant confirmed galaxy ever found, a record Carniani and his colleagues predict will eventually be surpassed. But for now, it stands as humanity's farthest view into the past, a window onto a universe 13.5 billion years away. Part 6. The problem with early galaxies when the Standard Model bent. Jade's GSZ 14-0 was not an isolated anomaly. It was the most extreme example of a trend that had been building since Webb's very first science images were released in July of 2022. Within weeks of those first images becoming public, teams of astronomers began combing the data for high redshift candidates. The competition was intense. Numerous groups were analyzing the same publicly released images, applying their own reduction pipelines and photometric classification methods, racing to identify the most distant objects in Webb's field of view. What they found, with a consistency that quickly became impossible to dismiss, was that there were significantly more bright galaxies at high redshifts than the theoretical models had predicted. Not slightly more, not a marginal discrepancy. Substantially, dramatically more, by factors of 10 or more in some redshift ranges. One astronomer at the Scuola Normale Superiore in Pisa, Andrea Ferrara, described his team's reaction when the first JWST data arrived. They had expected to see perhaps one genuinely red, high redshift galaxy at a redshift of 9 or higher in the early data. Instead, they found a cascade of them. The initial weeks were chaotic in the best possible way, filled with excitement and vigorous argument about what exactly was being seen, how reliable the photometric redshifts were, and what the findings might mean. Rohan Naidu, a young astronomer working late one night analyzing the first Sears survey data from JWST, describes the experience of finding one of the earliest galaxy candidates, a galaxy his algorithm flagged as inexplicably massive and dated to only 300 million years after the Big Bang, in terms that capture the texture of scientific discovery at its most raw. He called his girlfriend over to look. He sent messages to a collaborator with, in his words, many exclamation marks. The galaxy was initially calculated to have a redshift of about 16.7, which would have made it by far the most distant object ever confirmed. But subsequent spectroscopic follow-up revealed the photometric estimate had been off, and the true redshift was somewhat lower. The initial excitement faded into a more measured finding, but the pattern it exemplified was real. The standard cosmological model, technically known as the Lambda Cold Dark Matter Model, or Lambda CDM, describes a universe whose large-scale structure and evolution is governed primarily by dark matter, dark energy, and the physics of ordinary matter emerging from the conditions of the Big Bang. It had been tested against observations for decades, with remarkable success. The spatial distribution of galaxies, the acoustic oscillations in the cosmic microwave background, the expansion history of the universe, all of these matched the Lambda CDM predictions with extraordinary precision. The model predicted, fairly specifically, how many bright galaxies should exist at each redshift, and how massive they should be. Those predictions were calibrated against the Hubble Space Telescope's deepest observations. Webb broke those calibrations. The number density of bright galaxies at redshifts above 8, 9, 10, epochs corresponding to 500 million years after the Big Bang and earlier, was higher in Webb's data than Lambda CDM models had predicted by factors that, in the most extreme cases, reached tenfold or more. The question was immediately raised. Was the model broken? Had Webb found evidence that cosmology needed to be fundamentally revised? The headlines were dramatic. Some suggested the Big Bang itself might need to be rethought. The scientific reality was more nuanced, and the community worked through it rapidly. Part of the overabundance, as one study from the University of Texas at Austin, led by Katherine Chworovsky and Stephen Finkelstein, demonstrated, could be explained by the presence of active black holes in some of these early galaxies. The so-called little red dots, compact, extremely red objects found throughout Webb's deep fields, appeared to host rapidly accreting supermassive black holes. The heated gas and dust around these black holes emitted light that made the galaxies appear to have far more stellar mass than they actually did. When these objects were removed from the sample, the remaining population of normal star-forming galaxies was less dramatically in tension with the lambda CDM predictions. But less dramatically in tension is not the same as no tension. Some excess remained, and while the team at Johns Hopkins University, led by Nashwan Sabti, used Hubble data to show convincingly that cosmological parameters themselves could not be changed enough to fully explain the Webb galaxy counts without also breaking the Hubble observations, meaning the fundamental framework of lambda CDM was not shattered, the astrophysics of how those early galaxies formed, and grew still needed explanation. The most compelling current hypothesis involves a combination of factors. Early galaxies may have converted gas into stars with unusual efficiency, perhaps because feedback processes that slow star formation in modern galaxies, supernovae blowing gas out, radiation from young stars disrupting star-forming clouds, were less effective in the denser, more turbulent conditions of the very early universe. Additionally, early galaxies may have had less dust than later ones, making them appear brighter at the ultraviolet wavelengths that dominate their emission. Dusty galaxies absorb their own ultraviolet light and re-radiate it at infrared wavelengths. Dust-poor galaxies let that ultraviolet escape, making them appear more luminous in the filters where high redshift surveys detect them. There is also the hypothesis of bursty star formation, the idea that very early galaxies formed stars not at a steady rate, but in violent, brief episodes, with long, quiet periods in between. During a burst, a galaxy would appear enormously luminous, its apparent mass grossly overestimated by models calibrated to expect steady star formation. After the burst, the galaxy would fade and become temporarily less detectable. This scenario, explored theoretically and increasingly supported by simulation evidence, would naturally produce a population of apparently overmassive early galaxies that is not actually as cosmologically challenging as the raw numbers might suggest. None of this resolves every question. The field is still active, still debating, still accumulating data with each new observing cycle. In November of 2024, a new paper published in Nature reported the spectroscopic confirmation of 3 extremely massive galaxies, each roughly as massive as the entire Milky Way, all in place within the first billion years after the Big Bang. These so-called red monsters were not little red dots with active nuclei inflating their apparent brightness. They appeared to be genuinely massive stellar systems, and their existence required that galaxies in the early universe had converted their gas into stars with efficiencies far higher than models typically assume. The team at the University of Geneva who led the work concluded that current models would need to allow for some mechanism enabling unusually efficient early star formation, without necessarily overturning cosmology itself. The standard model, as Stephen Finkelstein of UT Austin put it, had not been thrown out. But it was being fine-tuned, stretched, required to explain things it had not been designed to explain. And Webb was the instrument that forced the issue. Part 7. Worlds Beyond: The Hunt for Life and the Atmosphere Problem. Somewhere in Webb's long list of science objectives sits a goal so ancient, so deeply human, that it tends to make people fall quiet when they contemplate its implications. Webb was designed to examine the atmospheres of exoplanets, planets orbiting other stars, and look for signs of the molecules associated with biology, signs of life. The technique is called transit spectroscopy. When a planet passes directly in front of its host star from Webb's perspective, a tiny fraction of the starlight filters through the planet's atmosphere before reaching the telescope. Different molecules absorb light at different characteristic wavelengths. Oxygen, water, methane, carbon dioxide, ozone. Each imprints a distinct pattern on the transmitted light, a spectral fingerprint that Webb's instruments can detect and measure. For small rocky planets in the habitable zones of their stars, the region where liquid, water could theoretically exist on the surface. Finding the right combination of molecules could be the strongest evidence we have ever had that life exists elsewhere in the universe. Webb began testing this capability immediately. The spectrum of WASP-96b released in July 2022 was a proof of concept. A year later, in 2023, Webb turned its spectrographs on the TRAPPIST-1 system, a collection of 7 rocky planets orbiting a small red dwarf star about 40 light-years away. The TRAPPIST-1 planets have attracted intense astrobiological interest because several of them orbit within their star's habitable zone, and because their relatively close proximity to Earth and their transit geometry make them good targets for atmospheric characterization. Webb's observations of TRAPPIST-1b and TRAPPIST-1c both revealed essentially the same conclusion. These 2 innermost planets appear to lack thick, carbon dioxide-rich atmospheres. The MIRI instrument measured their dayside temperatures and found them consistent with bare rock surfaces with little or no atmospheric insulation. Whether the outermost, potentially water-bearing TRAPPIST-1 planets have atmospheres remains an open question that will require many more orbits of observing time. But the most dramatic and contested story in Webb's exoplanet science is the ongoing saga of K2-18b. This world, roughly 2.5 times Earth's radius and about 8.5 times Earth's mass, orbits a small red dwarf star called K2-18 about 124 light-years from Earth. It was discovered in 2015 by the Kepler Space Telescope, and it became a subject of enormous interest because it orbits within its star's habitable zone, receiving roughly the same amount of light from its star as Earth receives from the Sun. Initial Hubble observations confirmed the presence of water vapor in its atmosphere. Webb's first observations of K2-18b, conducted in 2023 with the NIR SPEC instrument, revealed a richer atmosphere than Hubble had hinted at. Carbon dioxide, methane, and a tentative hint of something else. Something that got astronomers talking in hushed voices. That something was dimethyl sulfide. On Earth, dimethyl sulfide, or DMS, is produced almost exclusively by living things, primarily marine phytoplankton. It is the molecule primarily responsible for that distinctive oceanic smell at the beach. It is metabolic byproduct. It is a biosignature gas. And in 2023, the Cambridge team led by Niku Madhusudan reported that their analysis of the K2-18b data showed a possible spectral feature consistent with DMS. They were careful and explicit about the caveats. It was tentative, at low statistical confidence, and could not be distinguished clearly from other molecules with overlapping spectral features. But the possibility was there. In April of 2025, Madhusudhan's group returned with new observations, this time using Webb's MIRI instrument. The new data, combined with the earlier NI-RSpec results, reached what the team reported as a 3 sigma level of statistical confidence for the presence of DMS and a related molecule, dimethyl disulfide. 3 sigma corresponds to approximately a 0.3% probability that the signal arose by chance. In science, the convention for claiming a discovery is 5 sigma, a confidence level of 99.99994%. 3 sigma is, in the language of physics, an intriguing hint, not a confirmed detection. But it was the best hint anyone had ever found of a possible biosignature in the atmosphere of an exoplanet orbiting in the habitable zone of a real star. The reaction in the scientific community was swift and mixed. The Cambridge team was careful in their language. Madhusudhan himself said repeatedly that the results were exciting but required more verification, that unknown chemical processes could account for the observations, that the inference of DMS as the source of the spectral feature depended on specific modeling choices. Within days, Jake Taylor of Oxford reanalyzed the data and concluded that the spectrum was consistent with a flat line, that the signal attributed to DMS was below the threshold of statistical significance in his framework. Other teams weighed in. A group at the University of Arizona, led by Luis Wellbanks, ran the signal against a library of 90 different molecules and found that more than 50 of them could potentially explain the spectral features. The strongest single candidate in their model was not DMS, but propyne, a simple hydrocarbon with no known biological source. The Cambridge team responded by expanding their own molecular library to 650 molecules and finding that DMS remained among the top candidates. The debate continued through the summer and autumn of 2025, accumulating nuance with each new analysis. By late 2025, the broad consensus was that the K2-18b data were genuinely intriguing, but not sufficient to establish the presence of DMS with scientific confidence. More observations were needed. More observing time had been requested. The question would not be resolved quickly. What is certain, regardless of how the K2-18b story resolves, is that humanity has reached a point where it is possible to have serious scientific debates about possible biosignatures in the atmospheres of planets 100 light-years away. That this is possible at all is a statement about where we now are as a civilization. Madhusudhan put it simply and beautifully. We have entered an era where it is possible to detect and debate potential biosignatures. This is unprecedented. Whatever K2-18b turns out to be, we are asking the question with real instruments and real data. The asking itself is a milestone. Webb's exoplanet science extends far beyond these high-profile debates. It has characterized the atmosphere of the hot Saturn WASP 39b in extraordinary detail, detecting carbon dioxide, water, sulfur dioxide, sodium, and potassium, providing the most complete chemical inventory of any exoplanet atmosphere to date. It has found the first clear evidence for carbon dioxide in the atmosphere of a sub-Neptune planet. It has measured the heat distribution on tidally locked worlds, revealing the ways that their climates might circulate, or fail to. And it has pushed the detection limits for atmospheric features on progressively smaller, cooler, more Earth-like planets, mapping out what future instruments will need to achieve to characterize rocky planets with genuine certainty. Part 8. The Cosmic Web, Gravitational Lensing, and the Architecture of Everything. There is one more dimension to Webb's work that deserves its own quiet space in this story. Not a specific target or discovery, but a method and a perspective that runs through almost all of Webb's deepest observations, like a hidden structure in the weaving. Gravity bends light. This was one of the central predictions of Einstein's general theory of relativity, confirmed in 1919 when astronomers measuring the positions of stars near the Sun during a solar eclipse found that their apparent positions were slightly shifted. The Sun's gravity had curved the paths of their light as it passed nearby. For a single stellar mass, the effect is tiny, interesting only as a confirmation of theory. But for the mass of a galaxy cluster, hundreds or thousands of galaxies, plus enormous amounts of dark matter, totaling a quadrillion solar masses or more, the gravitational lensing of background objects can be spectacular. Webb's very first deep field image of galaxy cluster SMAC S0723 was chosen precisely because the cluster's mass would act as a gravitational lens, amplifying and distorting the light of even more distant background galaxies. The arcs and smears of light visible throughout that image, those elongated, curved smudges of color, are not galaxies distorted by some artifact of the telescope. They are real galaxies, billions of light years behind the cluster, whose light has been bent around the cluster's mass like a river curving around a mountain. Some of the same distant galaxy appears multiple times in the image, at different positions, because light has traveled multiple paths around the intervening cluster, each arriving from a slightly different direction. This effect, gravitational lensing, is one of Webb's most powerful tools for studying the early universe. By pointing at massive clusters and using them as natural telescopes, Webb can magnify objects that would otherwise be completely undetectable, seeing faint, early galaxies that lie behind the cluster's mass as if through an enormous cosmic magnifying glass. The Lensing by L. Gordo, the Fat One, the most massive, distant galaxy cluster known, allowed Webb to see galaxies forming stars within dusty shrouds that would have been entirely invisible to Hubble. The Cosmos Webb Survey, the largest general observer program in Webb's first cycle at 255 hours of observing time, revealed approximately 400 gravitational lensing systems, the vast majority previously unknown, providing a census of how mass is distributed across a large region of cosmic structure. And not just visible mass. Webb's observations of gravitational lensing are, at their core, observations of dark matter. The bending of light traces the total mass in a region, including the dark matter that dominates the mass budget of clusters and large-scale structure. By mapping the pattern of lensing distortions across large surveys, a technique called weak gravitational lensing, astronomers can reconstruct the distribution of dark matter directly, without any assumption about what dark matter actually is. A recent analysis of Webb data covering the view of approximately 800,000 galaxies from the cosmos field produced what researchers described as the most precise map of dark matter distribution ever assembled from space-based observations. The cosmic web, that vast, three-dimensional filamentary structure that organizes all matter in the universe into threads and sheets and voids, is a dark matter structure that visible galaxies merely trace. Galaxies are not randomly scattered through space but drawn into the gravitational channels of dark matter filaments, clustering at the dense intersections where filaments meet. The Cosmos Web Survey and related deep field programs are, in a very real sense, mapping the skeleton of the universe, the dark framework on which everything visible hangs. There is something profoundly affecting about this that resists simple analysis. Webb is simultaneously looking at the most distant detectable past and probing the invisible majority of the present universe's composition. It is revealing both where things are and what things are made of, and when things happened. In a single image, one of those deep fields, teeming with thousands of galaxies in a patch of sky that would be hidden by a grain of sand held at arm's length. Webb has captured light from objects at almost every epoch of cosmic history. Galaxies that formed when the universe was hundreds of millions of years old. Galaxies that formed when it was 1 billion years old. Galaxies that formed when it was 3 billion years old. All layered together in a single frame by the geometry of cosmic depth. It is a photograph of the universe's autobiography. Part 9. What Comes Next? The Future. Written in infrared. Webb has years ahead of it. With fuel reserves potentially sufficient for 2 decades of operation, it will continue accumulating data, confirming and overturning hypotheses, finding things no one predicted. Already, in its first few years, it has transformed multiple fields simultaneously. Early galaxy formation, exoplanet atmospheric science, stellar nurseries and star formation, the structure of nearby galaxies, the properties of solar system objects, the behavior of active galactic nuclei. The breadth of what Webb has contributed in a short time is extraordinary even by the standards of great observatories. But we are, in every meaningful sense, still in the early chapters. There are specific questions that Webb's ongoing programs are designed to answer. The JWST team continues to observe, using NIR spec to obtain spectra of galaxies at redshifts, pushing toward 15 and 16, hunting for objects that existed even closer to the cosmic Big Bang than JD's GSZ 14.0. Theoretical models suggest that the very first galaxies, the progenitors of objects like JD's GSZ 14.0, should exist at redshifts above 15 and perhaps approaching 20. At those distances, the light from a galaxy would be stretched to the point where even Webb's NIR cam reaches its limits. Detecting these most ancient objects would require the longest possible exposures, hundreds of hours perhaps, combined with MIRI's longer wavelengths to build up the full spectral energy distribution of the targets. Each new such detection would push the known frontier of the universe back a little further, revealing the universe in an incrementally younger state. The question of how galaxies grow their supermassive black holes is another active frontier. Webb has discovered unexpectedly large black holes in very early galaxies, objects that seem to have grown to masses of millions, or hundreds of millions of solar masses within the first few 100 million years after the Big Bang. Standard models of black hole growth, which rely on continuous accretion of gas at a rate limited by the radiation pressure of the accretion process, struggle to explain how black holes can grow this large, this fast. Some theorists propose that the first black holes were not formed from the collapse of individual massive stars, as black holes normally form today, but from the direct collapse of massive gas clouds, entire giant molecular structures collapsing directly into black holes without passing through a stellar phase, forming seed black holes 1,000 times more massive than those produced by stellar collapse. Others propose that early black holes grew through rapid mergers with other black holes in an epoch when the universe was denser and galactic encounters more frequent. Webb's observations of early galaxy nuclei, comparing their luminosity and spectral properties to what different formation scenarios predict, are actively constraining which picture is more accurate. The exoplanet program is building methodically toward its most ambitious goal. Every planetary atmosphere characterized, every molecular signature measured, every comparison between the chemistry of different worlds under different stellar environments adds to the dictionary of what planetary atmospheres can look like and what they tell us about the planet beneath them. The TRAPPIST-1 system, with its 7 rocky worlds, is being observed over multiple years, accumulating enough transit observations to detect even faint atmospheric features. The question of whether any of the 3 habitable zone TRAPPIST-1 worlds retain atmospheres rich enough to maintain liquid water, and, if so, what those atmospheres contain, is being approached with the patience that the problem requires. The textbooks will be revised, not torn up. The cosmological framework, the physics of stars and galaxies and the Big Bang, the structure of space-time, all of that endures. But the chapters on early galaxy formation will need to be rewritten substantially. The sections on the first billion years of cosmic history will grow longer, populated with data where before there were only theoretical sketches. The paragraphs on exoplanet atmospheres will expand from a few tentative observations to a systematic survey. And somewhere in those paragraphs, perhaps within the remaining lifetime of the people listening to this tonight, there may be a sentence that no author of any astronomy textbook has yet had the occasion to write. A sentence that begins something like, "Observations with the James Webb Space Telescope in year confirmed the presence of," and then names a molecule that life makes in the atmosphere of a world orbiting in the gentle warmth of another star's habitable zone. That sentence has not yet been written. The observations that will determine whether it can be written are happening now, photon by photon, transit by transit, year by year. Future telescopes will extend Webb's work. The Nancy Grace Roman Space Telescope, named for NASA's first chief of astronomy and scheduled for launch in the late 2000s, will survey the sky in near-infrared with a field of view 100 times larger than Webb's NIRCam. It will generate statistical samples of hundreds of millions of galaxies, mapping cosmic structure across enormous volumes, probing dark energy through the statistical properties of those galaxy distributions. The European Space Agency's Euclid mission, launched in 2023, is complementing Webb from a similar L2 orbit with wide-field optical and near-infrared surveys designed to probe dark matter and dark energy through gravitational lensing and galaxy clustering across billions of light years. On the ground, the extremely large telescope being constructed in the Chilean Atacama Desert, with a primary mirror 39 meters across, nearly 6 times larger than Webb's mirror, will eventually be able to characterize the atmospheres of Earth-sized planets orbiting nearby stars with a sensitivity that Webb cannot match, hunting for oxygen and water and methane together in the air of small, rocky worlds. But no telescope yet conceived or constructed will have done what Webb has done in quite the way Webb has done it. It arrived at the right moment, when computing power was sufficient to handle the data it generates, when astronomical techniques were mature enough to make full use of its capabilities, when the scientific community had been building toward its science questions for decades. It arrived after 25 years of preparation, delays, near cancellation, and faith maintained across generations of researchers. Engineers who began working on its mirror systems in their 30s were in their 60s when it launched. Graduate students who had trained in the hope of using it were senior scientists by the time their first programs executed. The telescope was a relay baton passed across 2.5 decades of scientific life, each generation handing it forward to the next. And when it arrived and unfolded itself in the dark, 1.5 kilometers from home, it worked. The JWST 140 Galaxy, existing when the universe was 2% of its current age, pouring out the light of hundreds of millions of suns, already enriched with oxygen forged in stars that lived and died before our solar system had any reasonable prospect of existing. That galaxy has been waiting there for more than 13 billion years. Its light has been traveling toward us for all of that time, crossing the expanding gulf of space, stretching and reddening as it went, a message sent before our planet existed, before the sun ignited, before the Milky Way had taken anything like its current form. And, on a night in January 2024, a spectrum appeared in data being analyzed by the JWST team, and someone recognized the fingerprint of the Lyman alpha break sitting at the position corresponding to a redshift of 14.32, and knew what it meant. We received the message. After 13.5 billion years, we were finally positioned and equipped to receive it. There is something in that worth sitting with tonight, in the quiet before sleep, in this space between wakefulness and rest where the mind sometimes opens to larger things. We are small creatures on a small planet orbiting an ordinary star in the outer reaches of an ordinary galaxy, in a universe containing perhaps 2 trillion galaxies. We have existed, as a recognizable species, for perhaps 300,000 years, a tiny fraction of a percent of the current age of the cosmos. And we have built a machine the size of a tennis court, with a mirror made of beryllium coated in gold, and sent it 1.5 kilometers into the dark, and it has sent back to us photographs of the moment the universe's first lights turned on. Not metaphorically, not approximately, actually, really, physically. The photons that fell on Webb's mirrors on those January nights in 2024 had been traveling since before Earth existed. They arrived. We were ready to receive them. Human curiosity is many things. Sometimes beautiful, sometimes dangerous, often both at once. But in its purest expression, in the expression that drives a team of thousands to spend 25 years building a perfect mirror in the hope of seeing something no human eyes have ever seen. It is one of the finest things about us. It is the thing in us that builds libraries and writes symphonies and maps the human genome, and looks up at the night sky with a question that will not leave us alone. What is out there? Webb is that question made physical. It is a letter written in gold and light and mathematics, addressed to the universe, asking, "What are you?" And the universe, patient as only very old things can be, is answering. Somewhere, the light from a galaxy we have not yet found is already crossing the space between us. It left its source in the first 200 million years after the Big Bang, perhaps even closer to the beginning than JADES-GS-Z 14-0, red-shifted to wavelengths near the edge of what Webb can detect. It is arriving, photon by photon, at this very moment. And maybe, in the years ahead, Webb will capture enough of those photons to tell us what galaxy sent them, to show us, in the data, the image of the first stars that ever burned, the universe's first light, the moment before the Dark Ages ended. That is what we are working toward. That is what Webb is for. If these journeys through science and the cosmos help you find rest and wonder in equal measure, a quiet like and a gentle subscribe make sure these stories can find you each time you settle in for the night. Sleep well. The universe will still be there tomorrow. All of it. Every galaxy, every star, every planet threading through its orbit in the dark. And somewhere in that darkness, about 1.5 million kilometers from home, a golden mirror is still open, still listening, still sending back the light of things we have never before seen. Good night.